So in this video, we're going to be talking a little bit about bond enthalpy. So bond enthalpy is the amount of energy required to break 1 mole of the stated bond used to measure the strength of the bond. So whenever we're talking about breaking a bond, if a bond is really strong, it's going to take a lot of energy to break that bond. Make sure that you know that they're always endothermic because breaking a bond requires energy, and we're going to have to put energy into the system to break these bonds. And the average of bond enthalpies can provide us an estimate of our enthalpy of our reaction. How we're going to solve for the enthalpy of reaction is our bonds broken minus our bonds formed. But here are some reminders that we need to take into account. If you have multiple bonds between 2 atoms, all of those bonds must be broken as a whole. So let's say I had a triple bond and I'm going to end up with a double bond. I can't just break one bond to make it a double bond. I have to break all of those, that one triple bond, and then I have to form the double bond. Because as I increase my number of bonds, my amount of energy I have to put into it does not increase linear. So you have to take that into account. And you can't break single bonds. You have to break all of the bonds as a whole. So our enthalpy of reaction, we said that this can be estimated by comparing the enthalpy of bonds broken with the total enthalpy of the bonds formed. So our equation is going to be that enthalpy of the bonds broken minus enthalpy of the bonds formed. I encourage that you draw out your structures because sometimes just looking at a formula can be difficult to kind of see what type of bond you have in a reaction. So if you look right here, we have methane and chlorine gas, and we're going to break one CH bond and break one Cl-Cl bond, and then we're going to make a carbon chloride bond and a hydrogen chloride bond. So we have to take into account which bonds we're breaking and which bonds are formed. You can break them like this. Also, if you just want to break every bond and then form every bond, it's going to give you the same answer. Again, since enthalpy is a state function, it doesn't matter how I got there, it's just that I got there. So if you just want to be safe and break all of the bonds and then reform all of the bonds needed, you can go ahead and do so. But I do encourage that you draw out the Lewis structures. So let's go to a practice problem. So in our practice problem, it asks us to estimate the enthalpy change of nitrogen gas and hydrogen gas going to NH3. So again, I encourage that we draw out our Lewis structure. So for N2, nitrogen has 5 valence electrons. So if I have 2, I'm going to have 10 total valence electrons. So whenever I'm drawing out nitrogen, we don't have a central atom because there's only 2. So we're going to draw one bond between them, so that is 2 electrons, so I have 8 electrons left. Well, if I surround one nitrogen, I'm going to have 6 electrons used. So I'm left with 2 electrons. And if I put those 2 electrons on this nitrogen, it's missing its octet. So what we're going to have to do is move some electrons around to make sure that both nitrogens have a full octet. Well, if I move 2 of these lone pairs in and I get a nitrogen-nitrogen triple bond, then this nitrogen has a complete octet and this nitrogen has a complete octet, so I'm finished. So in this case, it's kind of difficult if you were just to look at N2. I could be talking about an N triple bond, or if you didn't know the Lewis structure, you could mistake it for an N double bond. So make sure that you're drawing out these Lewis structures because what type of bond it is going to affect the energy that it has. So since we have that done, we're going to have 3 H2. Well, hydrogen only has 1 valence electron, so all of our H2 are going to just have 1 bond between them. And again, hydrogen's one of those exceptions that it has fewer than an octet. It can have 2 electrons and be satisfied. So all of these are happy. And we're going to say that goes to NH3. Well, nitrogen has, again, 5 valence electrons, and hydrogen only has 1 for each. So total, I'm going to have 8 electrons. Well, hydrogen never goes in the middle, That's one of our Lewis structure rules. So if I have this, I'm going to have 6 electrons for the bond, and then I'm left with 2 electrons to satisfy nitrogen's octet. So now that I have that, I'm going to have a total of 2 NH3s in my product. So to get from our reactants to our products, we're going to have to break bonds. And again, if you feel uncomfortable trying to figure out which bonds you have to break, you can break every single bond and reform every single bond in the product. In this case, it's going to be necessary to do that, but in some cases, you don't have to break all of the bonds. It really is up to you, but make sure you know what type of bond you're breaking because it will affect the energy and it will affect the delta H calculation. So again, our equation tells us the sum of our bonds broken minus the sum of our bonds formed. And that gives us our delta H of reaction, approximately. It's an estimate. So I'm going to break this nitrogen-nitrogen triple bond, and I'm going to have to break 3 hydrogen-hydrogen single bonds. So in our bonds broken, my nitrogen-nitrogen triple bond is 941 kilojoules per mole. And my 3 hydrogen single bonds are going to be 436 kilojoules per mole. And I'm going to subtract, and I'm going to put brackets just to make sure that I know that I'm subtracting everything. And this is going to be our bonds formed. So in this case, the bonds that I formed were 6 nitrogen-hydrogen single bonds. So our chart up there tells us that a nitrogen-hydrogen single bond is 391 kilojoules per mole. And again, we're multiplying that by 6 because we had to form 6 of those. So whenever I plug this into the calculator, I'm going to get 941 kilojoules per mole plus 1308 kilojoules. And at this point, we can take away our moles. We're just having minus 2,346 kilojoules. Actually, we're going to put the kilojoules per mole back in there because, again, this is for every mole of N2 gas that I burn or that I react, or if I wanted to divide by and find the products, then I would divide by 2 because there's 2 moles of NH3 gas formed. So now I have 2,249 kilojoules minus 2,346 kilojoules. And now I'll have negative 97 kilojoules per mole of N2, or I can divide this by 2 and find the delta H of reaction for every mole of NH3 formed, whatever your question is telling you. So again, make sure that you're writing out your Lewis structure. I encourage that you draw out all of the bonds. If you feel uncomfortable trying to figure out what kinds of bonds you need to break, you can break every single bond, but just make sure you're reforming every single bond. So sometimes you might be breaking a bond that you're going to just make it back again if you don't have to break all of the bonds, but whatever makes you feel comfortable. I encourage that with your Lewis structures or any sort of reaction that you're working with, I know at this point in the semester y'all have worked with a lot of different reactions, try and draw them out and try and estimate the delta H of the reaction. You have your appendix in the back of the book. You might have a little chart, and you can kind of compare that with other things that you've talked about. So I encourage that you go through and work through these practice problems.